Welcome back to Physics 142. We've been talking about circuits and different elements in circuits. Specifically, we've been focusing a lot on capacitors, these devices that store electric potential energy. In this video, I want to give a couple definitions, specifically first of dielectrics, which end up being things that help make capacitors better at storing electric potential energy. And then I also want to think about the concepts of current and resistance, two other important concepts for thinking about circuits and electrons and charges flowing through circuits. So let's dive in and first think about what dielectrics are. Basically, so far when we've talked about capacitors, we've just talked about a capacitor as a couple of plates, like metal plates, with just, we've thought of it as basically nothing in between those metal plates, maybe vacuum in between those plates. And so between those plates, if you have a positive charge and a minus charge, we get an electric field, right? That's sort of our picture of a capacitor. But if you want to ask the question, well, how much charge can you actually store here? What sort of sets the limit for how much charge you could store? Well, the thing that sets the limit is at some point you'll get so much charge built up that the attractive force between the two plates will actually pull particles off of one of the plates and have them jump over to the other plate, right? So that's a concept where we call dielectric breakdown. Basically, when the charges start flowing from one plate to the other plate. And the way to sort of prevent dielectric breakdown or make dielectric breakdown happen after having more charge is to put insulating material in between these two plates. So what we can say about dielectrics is that the ability of a capacitor to store charge and thus energy can be enhanced by adding a dielectric, some sort of insulating material. So insulating material, i.e. dielectric. So mathematically, how we represent dielectrics is basically what's going on with an insulating material is, well, when you put an insulating material in here, you have the particles in the material will tend to create an electric field that actually opposes this electric field, right? So any negative particles in the material will tend to sort of orient themselves towards the positive, and positives will orient towards the negative, and so you get sort of an opposing electric field. And so what happens in a dielectric, what we can write down, is that the electric field gets reduced. So if the original electric field without the dielectric, if we call that E naught, all right, with a dielectric, we say that the electric field needs to go down, so we need to divide by some number. And the number that we divide by gets this value K. The value K is the letter that we use for dielectric constant. Dielectric constant. And the dielectric constant depends on the material, right? So, depends on the properties of the material. So vacuum has 1, air has a dielectric constant just a little bit more than 1. I think K for air is something like 1.00059 at 20 degrees Celsius. Maybe something like glass might have a little bit higher dielectric, right? So something like glass might be in the 5 to 10 range. And the dielectric constant is just a ratio value. It's just how much the electric field gets decreased. So it's unitless, all right? And you can look up different dielectric constants of different materials in a table. Now, how this helps with the capacitance is, well, if the electric field goes down, if we remember how that relates to electric potential is walking some path through an electric field, right? And so if you make the electric field go down for walking the same path, that's going to make the electric potential go down. And if it just goes down by some constant, that comes out of the integral. So what happens is that whatever electric potential you had originally, that also gets reduced by the dielectric constant. And if we recall our definition of capacitance was that it was Q divided by V. Q divided by V. So if V gets smaller, right, if we make V smaller, then that will increase the capacitance. So by decreasing the electric field, we decrease the potential and we increase the capacitance. That's what a dielectric does. All right. So that sort of wraps up our discussion of capacitors, how you make powerful capacitors. Capacitors are these great devices for storing electric potential energy. But there are other important concepts when it comes to circuits that we haven't thought about so far. So far with capacitors, we've basically just thought about the capacitors as being fully charged, carrying that potential energy. But clearly we need to think about how particles flow to those capacitors through wire, and we need a mathematical way to think about that. So the way that we think about the flow of charges in a circuit is with the concept of current. All right, and basically current is the rate of flow of charges through some cross-sectional area. So what do we mean by that? Well, if you have, say, some sort of wire or something like that, or really anything, and that has some area, that any charges, however many charges are going through that area, say per second, that is our idea of current. Right? So current is our way of thinking about the motion of charge from sort of one region to another region. How we write that down mathematically is current gets the letter I, is the letter that we use for current. And basically it's an amount of charge per time, right? And so amount of charge per time, that would be delta Q, however much charge, Q over T, or in sort of calculus, if we think about a really small amount of charge moving in a small amount of time, we would write this as dq dt, right? And that's the rate of change of charge from going through some area, right? The rate that it flows is dq dt. That means that the units for current, are going to be the units of charge, which is a coulomb divided by time, a coulomb per second, right? Coulombs per second. And this gets a special name, which we represent with the letter A, when A stands for 1 ampere. All right, so current is measured in amperes, which is given with the letter A. I should make a couple other notes about current, that sometimes people will also, rather than talking about current, they'll talk about current density. And so you'll notice here we haven't taken into account the area. If you want to actually take into account the area that you're flowing through, then we talk about the current density, and we use the letter J for current density, and J is going to be the current, the dq dt, divided by area. All right, and so this is the current density. The last comment that I should make here is about the direction, is that as a matter of definition in a circuit, we always define the direction of current to be the direction of flow of positive charges. So I should say the direction of current is always defined to be the direction of flow of positive charges is sort of our definition of the direction. And, we know that actually in wires it's the electrons that move, but for historical reasons, we've always taken the direction in some current to be what direction positive charges would flow. So that is from positive to negative. All right, so that is the concept of current. One more definition or concept for us to think about here is the idea of resistance. So what's the idea of resistance? Well, we know that if you're flowing through a wire, that wires aren't actually perfect. That, what's happening when electrons are flowing, your atoms are going to be vibrating a little, and so they'll knock some electrons sort of out of flow. And take some of the energy from some of those electrons. So when the electrons are flowing through the wire, they're going to, over time, lose a little bit of energy. And so since materials which have current flowing through them lose a little bit of energy, we want to be able to quantify what that loss is. So the way we quantify that is we quantify that with this idea of resistance. So resistance, what should I write down? I'll write down that we want to think about losing energy. So electrons lose energy as they flow through a material. And resistance then is the way that we quantify the tendency of a material to make that energy loss happen, or we say to sort of resist flow of electric current. So resistance is this idea of losing the energy. Basically, it resists flow that keeps the electrons from taking that energy from one spot to another spot. So mathematically, how we think about that is we use the letter R for resistance. And basically, we need to think about how much energy gets lost, but it's not exactly energy, right? When we're thinking about currents, rather than thinking about energy, we think about electric potential, right? Energy per charge. And so it's however much energy you lose per amount of current that you let flow through the object. So resistance depends on how much current you have and then how much energy loss you get per current. That means that the units of resistance must be volts, the units of electric potential, divided by amperes. And of 1 volt per ampere, or sometimes amperes are referred to as amps, gets a special symbol, capital omega, which is 1 ohm. All right, so resistance is measured in units of ohms. We'll think a little bit more about resistance mathematically in future videos, but hopefully this gives you a few useful definitions that we can use in talking about circuits in the future.